really my pleasure to introduce Chukwubuikem Felix Amaefule, who's the person and the certified Autodesk instructor who's going to lead us through the session this afternoon. And Felix is the founder and CEO of one of our Autodesk learning partners, Generative CAD Services in Nigeria. And he's worked on a lot of projects within the manufacturing industry. A lot of them have been centered on delivering training and implementation support, especially with the Fusion 360 platform. So Felix is really one of our most experienced instructors here in the region, who's delivered training on Fusion with a particular emphasis on designing for additive manufacturing and the goal of moving into tangible production. So that hopefully gives you a good overview of what we're going to cover this afternoon. As I mentioned on the previous slide, if you have any questions, we have the chat and Q&A functions up and ready as Felix goes through his presentation. You may also be asked a few short questions yourself. We just want to understand your previous experience and understanding of some of these concepts as we review. Now, with that said, I'd like to welcome Felix. Thank you for being with us. And I'm going to hand over this session to you to take us through the presentations.
Thank you so much, Thomas, for getting it started. And thank you everyone for taking the time to be here. On a quick one, I will just quickly share my screen and then we can proceed. But just to be sure of what we're going to be doing today, this today will be a progression between what we have done on the first day, yesterday, morning session today, that we're going to translate into what we're going to do this afternoon. So it's really something that we're kind of building a layer from what we have done already. So first we will start with design for additive manufacturing, and then we will now go into the demo section. So this is more like the agenda for section, 2 sections we're going to have. And so it's very important that I will be making reference to some of the sections in the past so that we can also connect the dots. For some people who have just probably didn't join the early section, morning section, I'll also be trying to explain some concepts that everyone will definitely be carried along. Once again, welcome everyone for this section, and I'm going to get started. First, the first section that we're going to take is design for additive manufacturing. So we're actually going to go to the design guides, the slicing guides, and how, from the thinking process, when you're designing something and you have in mind of getting it out or printed or maybe manufactured through the printing,
I think we may have an interruption.
Can you hear me?
Yeah, Felix, there was a slight interruption, maybe 10 seconds. So, but now you're back. So I think it's okay now.
Okay. Thank you. So the next thing I wanted to just for us to go ahead is just get started. So next is I wanted us to look at the classification of manufacturing techniques. Basically, I think some of the questions we asked, you've seen that three major classification of manufacturing techniques. You have the formative. Inside the formative, you have the injection molding, casting, stamping, forging, and all that. And we have the subtractive. And in the subtractive, we have things, getting to lies. It really lies in between formative and are typically made from functional materials, particularly metals. So, and then you have to talk about the formative, which is best suited for high volume production of the same parts, requiring large initial investments in tooling like the molds, but then being able to produce parts quickly and at a very low unit price. So it's really kind of what's now really additive manufacturing. So we'll talk about the AM. So it's really best suited for low volume to have it used. Okay, you can also use it a little bit in mid-volume production, especially when you have 3D printing farms. So it's really best suited for low volume, complex designs that formative and subtractive methods are unable to produce. Or when a unique one-off rapid prototyping is required, when you just want to get something out, it's really required, and currently leading the trend for mass customization. So when you hear about mass customization, being able to iterate and get things out quickly and as quickly as possible is really something that gets out there. So let's move. Now, inside the additive technologies, there are quite a lot of additive manufacturing. Even though some of us who know a bit of additive manufacturing, more FFF, which we are going to pay more attention to today, but just for us to know that about 6 broad classifications of additive manufacturing. There's the FFF, there's the material restriction, that's fused filaments application, the SLA and DLP. SLA is material jetting and on the whole rest. So it's really something for us to know that FFF or FDM is not the only additive manufacturing technology we have out there. So let's just get to quickly to understand also the major benefits of AM. It's very critical to understand that when you talk about AM, there's actually a very huge benefit that it comes with faster innovation and time to market, which actually leads to quicker production than conventional manufacturing, from concept to a prototype to a final product. 3D printing test ideas and designs quickly. It enables you to compress design cycles by 3D printing multiple prototypes on demand. So you can actually do some iterations quickly and get it to print and come back, because there's no tooling. You can just, in a matter of minutes, have 1 or 2 iterations, send back to printer, you get it going. So another aspect is unlimited shapes and dimensions. So 3D printing takes this challenge of designing geometrically complex shapes with ease. And there is not much the technology can't do with the proper support material. So it's really something that, when it comes to complex shapes, unlimited shapes and geometry, even when it looks so complex, with the right support of materials, you can actually get it really printed and really in a good shape. So another is when it comes to low startup cost, which is what we call the low investment, startup investments. So it's really because it doesn't require tooling and is essentially there is no startup cost. The cost of 3D printed part depends on the amount of material used. So it's more like the time it took to the machine to print it and really the post-processing that comes out of it. The removal of the supports, the sanding, or priming, or the curing aspect, and even the finishing, the polishing aspect. So lastly, on the fourth one, they are low material wastage. Unlike when you talk about subtractive, I had to get to remove material before a shape from a block, a metal block. 3D printing really deposits, materials where it's needed. So outside the support, practically there's no material waste. Or where you can find the material waste is where when you're printing with support. So, so it's very, very important that we understand these benefits and how we can actually take advantage of it. And then when we talk about more mass customization. So it actually really empowers mass production of customized products. So you want to get especially for premium products, it's really also great that I could just have a product, slight modification to it to customize to a particular need and straight out without having to go through the process of expensive tooling of molds or trying to get really, wasteful process of this, subtractive technology like CNC processes and all that. So, okay, so going further, let's look at it from the point of economies of scale. So when does it make sense to consider additive manufacturing, from the economics point of view? Because it doesn't mean additive manufacturing have all these benefits. Doesn't mean it's it should be used for everything. So when you talk about manufacturing, you should be talking about only additive. No, but it's really how to look at it from the point where it makes sense, where it can be offers more value or the best value for you. So it's really critical that we understand that. So we're looking at the economies of scale. So cost is often the governing factor behind how parts will be manufactured. So the graphical image we have here gives a general insight into how the cost of manufacturing, that's the cost per part, varies based on the amount of parts being manufactured. Another important limiting factor behind this is whether a design is able to produce by a particular manufacturing technique. So, there's some designs that really can be produced by that particular manufacturing technique, any other except one. So in that aspect, you're really constrained to that particular manufacturer, whether it's costly or not. But when you look at a design that can be manufactured for maybe 3 or 4 different manufacturing or 2 or 3 different manufacturing technologies, then cost is really one thing that you really want to look at. And the volume also, cost and volume really goes in very so like hand in hand. So next is, I know this was slightly called the money section on the presentation about 3D printing, but just for the benefit of people who are just joining this section, and also to drive in certain things that we're going to do this afternoon. So I really want to go through it again. So it's important for us to know that while there are many different 3D printing technologies, the following sections will focuses on the general processes from design to final. So these 5 processes are, common to all 3D printing AM technologies, basically. So although each method of 3D printing produces parts in a different way, the core steps are constant across all technologies. So it's very important whether we're talking about FFF, or whatever we're talking about SLA, DLPs, SLS, and the rest. So it's important. And understanding that a lot of people here are young people who also understand students, professionals in the industry. So it's also very important to look at the career opportunities in AM. And from what we have here, so whether it's from software development, the slicer you're using, the fusion is from the point of the printers itself, from the electronics, mechanical enclosures for the printers and mechanical, material science, 3D printers are almost useless without the data that's been supplied from the design file and the materials. So if you don't have filaments or you don't have the materials to feed in to the printer, it's just almost useless. So the technician and the service engineers, so 3D designers, like went through yesterday afternoon section, or getting to designing drone, to technical sales, marketing, account management, educators and researchers and technical writers. A whole lot of blogs are talking about 3D printing, and it's quite so many, so many platforms and so many opportunities that AM offers. So it's as huge as well as really that new technology that we're hoping to really affect and progress the world civilization. So let's move into a section where we really kind of touched a little bit about all the whole general concept about 3D printing, to understand what really 3D printing is, the benefits and all that. But really just get into the design consideration for it's very, very critical that we start understanding how can we, while we are designing or while we are slicing, what are the guides? So what we are going to talk about here is for FFF slicing guides. So what are the guides, while we're slicing, what are the things, considerations we need to take note while we, get engaged into our slicing. So one I wanted to start here is the layer height. A lot of us know 3D printing, and we, some don't know, but, basically, from the money section, and the speaker mentioned about the layer by layer method that's 3D printing adds, unlike the subtractive, like most material, to keep adding layer by layer. So you can see on an image on the screen here, you definitely see that it's kind of layer by layer. But one critical thing that you are going to notice is if you have a layer height of 0.05 and 0.2 and 0.3, it's kind of quite obvious, to see. And so basically, at the most basic level, when a part is printed, with a smaller layer height, it will have a smoother surface and be able to produce finer details to a higher accuracy. Let me go back again to also explain that again so that we really understand. It's very, very, very critical for us to understand. When a part is printed with a smaller layer height, it will have a smoother surface and be able to produce finer details to a higher accuracy. But when a part is produced and the layer height is increased, it produces finer details. It's when the layer height increases, it's actually produces rougher details. Like, you can't see the surfaces get rougher, but it really helps for you to reduce the printing time. So why does it really affect the printing time? First is where your slicer slice each level of the layer height. So if you are using, let's say you sliced with 0.2 and it gave you different layer heights of different layers of about, let's say 100 layers, and then you slice in with 0.1, it means that you're going to be doubled. So it means that your printer will go through different axes of Z as you keep moving up and up. So it's really critical that we understand that that's also really multiplies the time it takes to print. So as your layer height increases, the time to print decreases, but also the surface finishing really gets worked on, really reduces and kind of gets rougher. So, but again, it also really implies that the layers may appear very visible when you use higher layer heights, like 0.3, just like we can see on the screen. And it's also very important that the relationship between view time and layer height is linear. So it means that when you're having your layer height is increasing, it means that your printing time practically, is decreasing, but your surface finishing is getting rougher, not finer. And you're also probably going to be having issues with printing tiny details in your parts. But when your layer height is decreasing, your printing time will increase. But that's also give you finer details. So it really is something that you need to know when to use which and how to use which. It's very, very important. We'll also talk about that. So one critical area also we really need to understand is the shrinkage and warping. Now, when I mean the shrinkage and warping, when it's typically associated with two mechanisms, temperature and curing. Temperature, before you print, your filament gets into the shoulder and the shoulder is already elevated at, if it's PLA, it's elevated at 190 to 210 or 215, and its ABS is probably around 230, 240, 250. So it's really going to quite high temperature, 250. Yeah, for ABS is around 230 to 250 degrees Celsius. So, and it's really quite a high elevated temperature. So because of that, that's what we're talking about, the temperature. Then the curing is when it gets printed, the temperature, remember, is at 200 for PLA, or let me use an average of 200 at pure PLA. And then it's likely going to be cooling. So the ones down will probably going to be cooling close to room temperature, but the one on top is really doing what? Is see coming at maybe 180, 150, or even 200 as the case may be. So that curing aspect of the ones on the lower surface is actually, as it's shrinking, it causes shrinkage. And for that shrinkage, it can start pulling out because it's cooling at a rate where the water is on different. So there's a quite large temperature difference between what is on top and what is already on the bed that probably have been printed about 5 minutes ago or 10 minutes ago. So it's really that aspect. And it's something that we're also going to talk about, the areas of how we can actually, mitigate the warpage and all that. But as one area of print cools, let me also repeat, it contracts. So when it cools, it kind of contracts. This contraction leads to shrinkage, of the build material. The contraction also pulls the surrounding areas, creating internal stresses. This is why filaments that print with 200, 230 degrees require enclosed volume and require heated beds. So when you are printing like ABS, you're printing like some material like ABS at high temperature up to 30, it's very, very critical for you to really consider, like for you to really print and come out, for your print to come out fine. It requires a printer that has a heated bed. So where you are printing, where the object is on top, the bed is heated, and it can get to some heated bed can get from 40 degrees to about 100. Some can get to 120 degrees. So that will really allow that, that temperature transfer, that the temperature difference between what is coming on top and what is on the ground is not going to get so wide. Another aspect is ABS printers, or maybe PHP, ETG, and some other printers. Mass filament also requires an enclosed volume. So the enclosure really needs to get close so that there won't be so much interaction with the temperature of the surrounding environment. So if you get an enclosed volume, it means that you can keep the temperature at a particular range and not really allow it to interact with, which will really going to affect the temperature inside the printing part. So if you're able to mitigate this, have a heated bed, and being able to have an enclosed volume, it's really almost 90% in solving, warping. So let's continue. So now this aspect, also one critical aspect that we're really going to see, even during the demo section, is support. So support is very critical. Sometimes you require support, just like what we have. Some of your designs might need support, some designs might need support. But it's very important for you to understand that support materials really comes into handy when you have maybe complex shapes, very complex shapes, and then complex geometry and all that. So it can actually, because the printer cannot build on the air, it has to build from the floor. So when you have a feature that doesn't have any support coming from the materials coming from up, support is quite very needed. And if you get to see here, you get to find out that in this place, you find that you have support in this particular direction. You will definitely need support. Without it, it will fail. So it's just for us to understand this. But this is the product we are printing. All this just to make sure that this printer with this orientation, we definitely need support. So it's very critical for us to understand support. Now, one aspect that will really be very critical while we are slicing, and that really also affects how our product comes out, how strong or how brittle or fragile the product comes out, is infill density, or we call infill percentage. So looking at the graphics on the screen here, you're having one of 20%, 50%, and 75%. So what's really is infill density? So as FFF, like this FFF or FDM, as we call it, prints generally not printed solid. So to save on materials and decrease build time, parts are printed with internal low density structure known as infill. So it's FF printers, especially FF printers or printing, really does not have a full complete solid inside. So but apps externally, the shells, external shells, we're definitely going to put inside of those shells are always like have infill. So, and the percentage of the infill of 20%, which is most time, that's what you have most printers between 15% to 25% as a default. So that's what really get to have in most printers by default. So especially standard. So, but when you want to increase you want to get something stronger and all that, you really want to get a different variation of the infill. So infill percentage is a parameter that can be varied based on the application of the parts. For high strength, parts can be printed 80% solid for high strength. So when you're printing high strength, parts can really be printed around 70, 75, 80% solid. If a model is only used for form and fit testing, if a model is just used for form and fit testing, the infill density can be decreased as low as 10%. So form and fit is just something you just want to get the proof of concept, or something you really want to get, does this fit in here? You're not looking at, how fragile it is or functionality, just really form and fit. Then you can print as low as, and this really also reduces your printing time. So the more you increase infill density, the more the printing time increases. So it's very, very important for us to understand that. So, again, if you want to have a kind of a common issue, like I pointed out, around 20% is a common issue intensity for FFF printing. So about some machines or 3D printers varies between 15% to 25% for normal standard printing in your settings that you have. You really want to alter in there. So again, layer adhesion. So just like the former earlier section we had, today, we talked about printing layer by layer on top. And the profile for filaments are all like circular. The circular is really circular. But when the print comes in on the bed, another print comes in. The next one coming in, that the second one, the third one, the fourth one, really presses down your print. So instead of having this profile, it ends up having this profile. So that also means that the profile here are shoots to get from this oval shape. So it means that you are having this error from your design because you're having this in is opposited, but this is how it's going to come out. So you're seeing from this direction here and here, and you're seeing this profile moving towards. So it's not coming as well. So you're seeing having this error margin because of the layer adhesion of this. So it's important to know that layer adhesion or bonding is an important part of printing, the printing process. So our filament is extruded, it needs to bond and solidify with the previously printed layers to form a solid cohesive part. To achieve this, the filament is pressed against the previous parts, press it down, and the hot extruder ends reheats and melts previously printed layers. The downward force of the partial reheating of the underlying material enables the bonding of the new layer with previously printed layer. So this is like the adhesion, but you also need to understand how this really affects your profile, especially when we come to talk about holes and how really this phenomenon is actually really affecting some of the features you might really be imputing into your design. Now, so it really means that FFF filament is actually positioned in an oval shape rather than in a circular shape, just like we're seeing here. So next slide, we're really going to talk about a little bit of functionality. Really just to check about, how prints come out and how really prints, for usage and functionality. So remember that, assuming that, your printing height of a printer is the x-axis, and then as it's printing, this particular design here is printed layer by layer and the direction. It's printed layer by layer. Then this also is printed from this direction, moving this direction. This is printed moving this direction. Now, what it means is if you are going to have a force, now really pay attention. If my print, like my design, is really going to undergo, let's say, tensional stress, right? It's going to undergo a tensional stress. And there's going to be a load attached here or a load attached here on both sides. Now, the weakest point of any 3D printed object is the point of adhesion, which is this layer by layer. So when you know the functionality and how that product will be used, now that's really going to let you know on how you orient your product or your model in the slicer to really make sure that it comes out fine. But it does not necessarily matter if it's not really going to be a functional product and all that. But if it's going to be a functional product that's really going to undergo in some loading, force loading and all that, it's very critical for you to understand this. So for this particular thing, you mean that this will easily break off, it will tear. So the best arrangement is to actually print this thing from this direction, like put this direction should be on the layer, on the bed, then print it this way. So allowing that weakest point is not at the axis of loading of the force. So it's very critical. But this is really going to test out. So it's something that is very important and very critical for us to note. that, you know, is something that while we are trying to, yes, we finish a design, but bringing it into it, we should also have in mind, bringing it into the slicer, we should also have in mind about how the orientation and how our object is functionality and all that, that we're really going to go coming into how we orient and how we put kind of add different slicing, you know, settings and all that, and some guys that can really get to have us. So now we're really going to go in into the design considerations for design, like why things you really should consider when you are in the design part. So most of the things we did here is thinking about the slicer, like these things are actually settings you need to, you know, consider while you are slicing your design. So let's move back now to why you are not doing that design. What are the things you are going to put consideration? Yesterday, we had a hands-on that had to guide us to how to model a part and all that. So while you are modeling that part, just like we had the section yesterday, what are the considerations, or what are the guiding considerations should you be putting your head of to be always look out for while you are designing? Because you know that this particular object of being modeled is going to be 3D printed. That's the manufacturing technology. So, because there are also rules that will really help you to get your print come out fine, or come out badly, or even totally fail. So first, what we're going to talk about is fillets. So, you know, fillets help to reduce stress concentrations at the corners and edges and make parts easier to print. You know, fillets should be included in the design of 3D printed parts wherever possible. It's very important. A minimum, pay attention, a minimum of 2 mm radius is a good starting point. So when you talk about your fillet, do not use anything less than 2 mm. So a minimum of 2 mm radius is a starting point. So for outer edges that are attached to the bed, the build plates, a 45-degree chamfer rather than fillet, is often better solution as it does not require any support material. Right? So we're saying this is the fillet and this is a chamfer. So when you're going to have this, let's say this is your bed, where the starting point of your bed. So this particular part is attaching to the bed, so it's best to use chamfer. But for this is fillet, you should use what? You can use your fillet. It's important that you can actually have edges, really chamfer. But the ones that are going to be on the bed, please, it's really preferred that you use your chamfer. It's important. And why, we're talking about chamfer is because also overhangs. So looking at the image here, you'll find out that, as your design is kind of having a small draft, it's moving at an angle, it's good, keep coming fine, but more it passes 45 degrees, it does what? It starts failing. So when you have an overhang that is less than 45 degrees, supports are needed. So really for our overhangs less than 45 degrees need support to produce accurate prints. Accurate prints with a smooth surface finish. Maintaining the 45 degrees limit is highly recommended. So the downside of support is it has a detrimental effect on your surface. As it's in contact. So the surface that your support is going to be in contact with, it's definitely going to get it rougher. So if you know that you can actually avoid the overhang, just don't even, try as much as possible to have your overhang less than 45 degrees. But if you can't, then you just be aware that when you print, you have to print with support for it to come out fine. And you also have to do a little bit more in post-processing by, trying to remove the support and also going further to, sand or doing sanding process to get the final, using final grades to get the final surface to really get something better, because those points where the supports are will really going to be rougher than the other areas where there is no support materials on the surface. So it's very, very, very important. So that's rough, surface is something that procedure. Now, this is also certain things to also draw our attention to when we talk about support. So this is a kind of a really perfect example of having an unsupported walls, not really printed down walls with support, and the ones printed with support. You're seeing that it's coming up fine. Just know that this definitely would, this surface where the support is attached will come out of. So the best way you could have printed this is maybe print with this part on top, turn it upside down, and you can actually have a build without any support, without having a fair end. Another aspect of that I really want to look at is the horizontal bridges. Just like the image in our screen, the graphic image in the screen also shows us. So when a bridge that's connecting, you have the two things, and then you're having the horizontal bridge connection running to two stands, depending on your product you are designing. When you kind of have a bridge similar to this running through something, and there is nothing under it, like a material under it that is being just kind of a bridge, definitely like it. So it's really important to know that less than 10 mm in length, if the bridge is less than 10 mm in length, support is not required. But if it's longer than 10 mm, please add support. Otherwise, that print will fail. Because of the printing speed of some printers, which started from the base print of 60 millimeter per second. So it could actually print, the shorter 10 mm is quite smaller. So you can actually use the speed to connect the dots without failing and without sagging. But if you have it more than 10 mm, then you really need to use support. Otherwise, it's really going to fail. So, so again, is in here, we are looking at another aspect of it, which we talk about the holes. Remember when we talk about the layer adhesion and the orientation of the hole. So in here, if I have a hole at this point, this particular design, it will really require some sort of support, otherwise it might start failing if I don't use support. So, but again, it's also important that if I'm printing on top here, you see that the surface in here is didn't come out well. But if it is a small of less than, practically less than 5 mm, 10 mm hole, then you don't really need to have support. But if you please do not use support anything less than 5 mm in here, because it's really going to be very terrible very difficult to remove the support, because 5 mm hole is very tiny. So, and it doesn't really require support to print. So please do not use support for such a thing here. But for larger holes, fine, you can use support, because the more larger, the more it can deteriorate, without support. But with smaller holes, please do not use support. 2 mm, 3 mm, 4 mm holes, please do not use support. But in here, it's important that you know that if you're going to remember that you're going to give a little bit clearance here because of the adhesion and the oval shape that is being created. So when a print comes in here, there's an offshoot here around of that oval shape instead of having a circular shape. So you may want to give a little bit clearance of about 0.1, 0.2 clearance in your design to be able to still get as an addition of 0.1, 0.2 to be able to accommodate that in your oval shape that was not put in place, from the theoretical, extruding to the actual extruding where it's coming out from, oval shape. So it's very important. So, and again, this is something that we really want us to really pay attention to. So these are like the kind of majority of the guides that we can really look at, from most of the things that I've said about design and all that is really here. One great thing is what I just went through here is basically for FFF or FDM printers, where you can also go through one of SLA, SLS, jet binding and all that. So you really get to see some rules on how we can see how, the table really gives us, okay, what the do's and don'ts, and kind of a guide for us to really come up with something, a design that we can send to anybody or 3D printing surveys and then it can actually push it in and slice and print without issues and returning back your work because you have done designs and you didn't really consider for manufacturing. And this thing is also very critical and applicable when you're designing for any other manufacturing technique, whether it's injection molding, whether it's sheet metal fabrication through CNC, and all that. These rules and guides are all applicable for each manufacturing technology. And even in within some manufacturing technologies, so also have some peculiar rules that are particular for the different technology. Like you have an additive, you have inside additive, you have different technologies inside additive, and then you have also specific rules depending on the machine itself. So it's very important for us to know this. So again, so we really want to have this quote for us to really understand what we're doing and why we are emphasizing this. So students typically get trained on using 3D modeling tools designed, but they are not given an experience of how to manufacture the design. This is really a huge gap that impacts the ability to successfully operate in the manufacturing space. So a designer, a design engineer needs to understand how to translate their design into efficient manufacturing processes of physical products. And this is why this section we just had now is important, because if you do not understand design for manufacturing, you are more like a 3D modeling person, or you can't really say you're a design engineer, because a design engineer designs something that is manufacturable, that gets into, like, you can design something and it gets sent to the manufacturer, the manufacturing technology, and it gets printed. And also, you're also understanding the usability, you're also understanding the cost implications and all that. So engineers are also cost modelers. So it's very important for really understand this, the forces that comes into this, for us to get a very, very practical and a very working design into what we're doing. So thank you so much. I think we pause for this section, and we're going to have a quick Q&A. But before we go through the Q&A, our questions and start answering questions, I think I want to go through the full questions again. So let's scroll launch and see really whether we're able to catch up something here as to what we had and what we went through. So please, I think it will really be something. Let's go through this. And so pool one, so we can just quickly run it through. And so at this time, I'm really going to be giving the answer. So at sheet one, so there's a picture of manufacturing technology. So yeah, the answer is C. So yes, additive manufacturing, right? So the answer is C. So for pool two, one of these is true about layer height. So yeah, so let's see whether we're able to catch up something from section, and whether we're able to kind of close that gap is really something that we want to get to. So, okay, I think counting down to the end of the pool two. Okay, so yes, the answer is A. For question two, the answer is A. The smaller layer height will have a smoother surface in print. So yeah. So for question three, that's pool three. Yes, as an engineer and product design, which of these manufacturing techniques is best suited for testing proof of concept and rapid prototyping? So I think nobody should be able to this, like everybody should be able to get this right? After going through this process and going through these sections, we definitely should be able to get these questions. Oh, awesome. You guys really made me proud. Yeah. So yes, the answer is additive manufacturing. Yeah, so let's get to the number 4. This is quite a little bit tricky one, but yes, we covered it. So for people paying attention, so how many core styles are constant across all additive manufacturing technologies? I think yes, it's one of the few things we cover. So let's see how many people will definitely get it right, and so how many people are also paying attention to it. So, okay, we are almost there. And oh, wow, that's 5. That is 5. The answer is C5. Like, you know, I really want to go through this process again. Like 5, 5, 5. Like it's really fast. So okay, I put 5. So one of these is the right way to mitigate warping in FFF. I think, this is something, the options are quite tricky, but you really pay attention to the section, you will definitely get the answer. It's something quite straightforward. And I really emphasized here, I think I really spent quite a lot of time on this section. So yes, I think, so, okay, the answer is B, which is, yeah, that's B. So ensuring water thickness and constant enclosed volume. I think I emphasized this when I mentioned of ABS and you know, ETG and some other PA and PC higher materials that really require, you know, higher temperature to print. So I think the next one is okay, number 6. Okay, so overhangs that are less than 45 degrees. Okay, this is, I think nobody should fear this, right? Nobody should fear this. You know, it's quite something I think we should be able to get, you know. So let's see who gets it. I think you should be able to get it like, okay, that's fine. That's fine. I think it's something that we agree. So the answer is actually A, does it need support to produce accurate print? Yes. So numbers proof 7. Okay. Which of these is true for infill density? Very tricky options, but I think, you know, I really paid attention and I really emphasize on this. So let's see who should be able to get it. You know, it's something that, you know, we went through in the process of infill density. When we look at the printing, the FFF, it does not really completely fuse, you know, and all that. So I think we should be able to have this. And this is the last question. So, none of the above is the answer, like none of them. So actually, what you have here is not for high strengths. You know, parts are printed in 10%, rather it's high strength for 80%. And then test and fit is 10%, not 80%. So it's actually none of the above, right? So you actually paid attention. Okay, so thank you so much. So I really want to take some time for the questions and answers to get to it. So Thomas,
yes,
do we have
thank you.
questions?
Thank you, Felix, for the first part here. There actually hasn't been any questions in the Q&A or chat from what I could see, but if anyone wants to ask something now, then feel free to use either the chat or Q&A box in Zoom. And if you don't, then that's okay, because we still have the second part of the, you know, the real workflow in Fusion directly, so maybe that generates more questions. And on top of that, we also have a Q&A section at the end, but I'm currently not seeing any questions. I guess everything was clear. Someone has raised their hand. If you want to put the question in the Q&A or the chat, because we are in, have muted phone lines here, so we can unfortunately not hear you. Okay, here we have, great. So first question, are the design considerations applicable to all 3D printing processes, such as SLA?
Yes, yes, and yes, they are all applicable to all, but not, okay, let me quickly share my screen to answer that so that it will be quite, you know, clear enough. Okay, so when you look at this, you find that this is for SLA, right? So you find that, you know, so you also see the design consideration. So what we went through was for FFF. So same thing that I went through here, you're also going to find it, right? So you're also going to find this in here. So this is for FFF, we went through FDM, we went through now. So for SLA, for metal and all that, you will definitely go into these also. So yes, you really need to look out for design considerations for each manufacturing technology, whether it's SLS, SLA, or DLP and all that. So what SLS and DLP are quite close, just a little bit change in the technology, but that does not really affect so much of the consideration. So you can actually use all considerations to go through. But yes, so yeah, you should really be able to look at it. So is that applicable for building materials? So building materials uses, there are different type of printers for construction. So quite large, big printers for construction. So yes, it's different. So, if you're looking at materials, it's a different materials. So in the construction industry, you're looking at concrete, and then put into extrusion and then it gets to pour into the process. So it's quite a different take. So what you also need to do, if you don't take anything away from this class, is to take away that while you are designing for something that will be manufactured, you need to really understand the design consideration and design guide for that manufacturing process that you're going to use. So yes, look out for that, whether it's injection molding, whether it's sheet metal fabrication or any other manufacturing method and all that. Really look out for the design manufacturing guides for it.
There was a question that came in before during we went for break, so maybe it's worth picking up on that and then moving on to the next section after it.
Yes, so I think the question was, are the tolerance applicable to both civil and mechanical engineering products? So yes, so there are different, tolerance, but when you are talking about tolerance, it's actually applicable on what you are designing. So, but yes, you have tolerance, you have to do GD&T depending generally. GD&T, one of the core aspects of design, GD&T, geometric drawings and tolerancing is tolerance. So it's certainly something that is applicable for every design. You really need to go to that, especially when you're looking at, putting it into consideration and something that will go into manufacturing. So whether it's additive manufacturing for the construction or even prefabrication for construction industry. So yes, this is applicable, but not this particular consideration. So each of them, like I pointed out, have their own design guide and design considerations, depending on how that will be manufactured or how that will be getting to from design to reality. So what you really need to do out is there are a lot of resources you cannot get out there, and you can also reach out. I can just point one or two things out to you, depending on the area of interest. But yes, there are particular design considerations for each application. So whether it's in mechanical or whether it's in construction or manufacturing, as the case may be, longer. So as far as it's a part, physical part, definitely that goes to manufacture, yes, there has to be that, those considerations, but peculiar to that manufacturing technology or to the industry.
Perfect.
So, yeah.
That's great. So I think that was the question we had coming in. So then I think we might move on to the next part of the session in that case.
Okay, so what I will do now is just to quickly share my screen, just to give our direction to where we are heading to now. Right, so let me quickly share my screen. So yesterday with Chris, we had the privilege and the honor to go through the drone design and how he was able to model like the model parts and all that. So today we also want to take that progression a little bit more. So as time will permit, we're probably going to take two different designs. So we want to go into explore additive. We're going to also explore we're going to explore additive, and we're going to explore generative design. Generative design, we're going to explore generative design, like how we're able to get out, a design that comes from generative design and a design that comes from normal solid parametric modeling. So that's what we're going to do today. So quickly, we'll go through this. This is the part that we got in, and this is where the interface where Chris was able to go through the process. So today, I'm going to take this part and moving forward to where we're going to talk about the additive manufacturing. Like, okay, start preparing this. Now, just to point out that all design considerations I have mentioned is very applicable here. While designing, the ones that are design guides and the ones for slicing, that's what's really going to go next for slicing. But the one for the design guides, these design considerations was considered in why this was done, right? Why this model was already in the model. So moving from here, I'm going to move from design workspace to manufacturer workspace. So you see that the UI changes and have different tools in here and all that. So first thing I need to do, and I just want to point this out, is I'm going to go through a process that first you can actually document the process. You can write them down if you want. So I'm going to be with highlighting each of the stages so that you can also want to write them down. And you want to also go through the process. Again, the videos will also be be shared. So definitely you can also go through the process yourself or go through the videos over and over again. So so first thing we need to do is just to switch from design to manufacture workspace, which we have done. The next one is to actually create a manufacturing model. Now, what this does is to actually allow us to disassociate from the design model, which is what we have here, and duplicate it to be like, oh, whatever changes we do on that manufacturing model will not affect our model on the design workspace. So that's why we're going to come here. So here and create a manufacturing model. So immediately we come here, we see this. So this is turned off immediately now, and then we are only seeing this, and automatically this is activated. So this is what we're going to work for our slicing. This is not like the manufacturing model we're going to use. It's really quite a first step that we should take. The next one, you should set up, click on setup, which will come down here to start the click setup to commence our setup and slicing process. So it's really the first point for us to start slicing after we create our manufacturing model. So when we click for setup, we're going to be pop-up here telling us in this we have tab here, setup, post-process. Now, in post-process is actually where we're going to finish slicing and we want to push into the point, the format that the printer can understand. So I can say, okay, I can say part 001. So let's come to understand this. Let's go back to the setup. And I will select the machine. The machine we're talking about is what printer do we want to select, right? Or do we want to print it? So I click on select. I'm coming here. You need to come here, please, because in yours, you will not have anything on your machine. So you come to the Fusion library. You will see all different material printer vendors out there. See the different. So I'm going to go to FlashForge and take FlashForge, right? So I can also come here and filter, take the additive is selected. I can say FFF only printers, and all that. So yeah, basically you have 3 printers. Fusion actually supports this manufacturing technology. So if I want to say, oh, I want to select this, so nothing here. Here, there's nothing. So there's no printer from FlashForge that exists. So if I go back to all, there's no printer here. I check. There's no printer here. I can see SLA, which is the printers here. So, and I can check and see there are also printers here. So basically, you will find that Fusion and support these printers. You can slice right from inside Fusion, right? So, and these are different technologies and all that. So, Fusion allows us to. So, but let's go back here and check and go back here, and then we'll come back here to FlashForge, and let's say, okay, we want to select the printer we want to use. So let's say, okay, FlashForge Creator Pro 2, which we kind of saw in the slides when I was presenting. So I'm going to click here and select. I'm going to click here and select. So automatically it brings kind of the volume of the printer, right? So one thing again, I want to go, let's come back and say, oh, I want to select my machine. So back, what I could have done is, why in here, let's say FlashForge, come back, I want to repeat the process, select. So you can see that there is a copy. There's a copy here. There's an export that's copy selected. So I can actually copy this instead of coming here to look for it every time. I can just copy it and come to my machine, under my machines, local, and paste it. See, it gets pasted here. That's how I brought this one. So I can also delete it and it goes out. So it's important that, okay, let me pick this up and delete so I can come back here and pick. Okay, pick, and let's say copy, come to local, paste. See that? So I have that. So what I need is just to come to my machine. And basically, I don't need to be online to be able to access this now because I have copied to the local Fusion. Whether I'm online and all that, I can see this. But if I'm not online, on Fusion Library, this is online, so I may not be able to see that. So it's very important that I can move this process and put into my machine here. The next thing I want to do is to set up the post-processor. So I can, if it's not set up right, so I can just come here and select a different post-processor. So you see FlashForge, there are actually two FlashForge. So it tells us here that post for exporting two parts to FlashForge Creator is in G code. This is basically for one that are only for Creator Pro only, but this one is post for exporting except for Creator Pro 2 and credits and all that. So if it actually stands for all FlashForge printers except this printer. So and the one I'm selected for is within this because it doesn't fall within this. So basically, so I can come here and then select and use from my lab. Okay. Come here, I've already selected it. So I can also come back here and select the printing settings, which I can do here, or I can just do select and come back here. You see the printing settings, something I can do. You see taking me to where I can select. So I can come back here. Remember, this is recent, which is something that I've done in the past. So for you, doing it first, you just need to come to your Fusion library. This is where you're selecting your materials. And then there is a standard layer height applied to it. And the manufacturing technology you're seeing is this, right? So, and this manufacturing technology is because of the printer I selected, which is FFF. So that's why it's showing me just FFF technologies. Now, back to this. So what I'm going to do now is to select what I'm going to use PLA. Yes, so just PLA 1.5 for filaments. So I'll just select, so it comes out here. The setup operation is additive. I need to check this so that I cannot 2D, make sure it stays in the X and Y in the bed. And then the model, remember, is a manufacturing model I just selected, so it has to be there as a component selected. And I say, okay. So it brings up, and immediately you see that there's new features added here. Immediately I brought the machine inside. So here I can rotate here to show you, what we just did now. So, okay. Let me just move around here. Okay. Okay, so, and I can just push this, or I can just come back here and right click and make sure, okay, send to, make it front, and I come back here and I say stop, right? Okay, I have that. So I can also come back here and say, okay, this is, I want to be like home, but use view. So I can just come here and it shows me the view of whatever I click here, it shows me this. So that's it. And what the next I can do is to come here and use components. So if I wanted to rotate this a different way, I can use this move to rotate around, depending on what I want to do. I can just use it to rotate around and say, okay, or I can use this to rotate this way. But because of the orientation of what we have, I can also use this to move front or backward, just to position this. So if I want to use front or backward, I can just pick here and then position here and make sure it also aligns to what I want. So that's where the move comes in, and I can just use it and come back here. So I can just use this up and down, or I can grab this around and get what I want. So yeah, so I can drag it here, But what I can do is just to position, have the rotation and all that, and I'm good. So it's hanging, right? It's not sitting on the bed, so I should not that concerned because I can use this place platform, pick it up, and then say, oh, do I want a clearance of this on the bed? If I say no, I just use 0, 0. I've started the components already. So arrange will make me look like for this to actually be at the center of X and Y axis. So arrange this to be kind of at the center. So I check it and I click. See it goes down. Automatically goes on the bed. And because this is flat, there's no features that we needed to support. So basically, we don't need support for this because this is flat and every feature is building start from the sky. So with this particular model, we don't really need to apply support. So what we're going to go through the process of the other one for the generative design, that's where we really need to get to support. So if you come here, you start seeing that look at the printer, we have signed the moments. And if I now wanted to check into the advanced parts of my slicing, what I just did is just a basic selection. And if I'm good with it, I can just come back here, right here, and say generate. Or same thing here, I can come back here and say generate. It starts slicing this product. It starts adding this model to show me the stuff. It's giving me an error saying, okay, one constraint to be. Okay, so basically what it's saying here that my design is too constrained on the bed. It's too very close on the bed. So I'm really having a kind of design. So I can come back here and say, oh, let's rotate it this way and see how that will pan out. Right, and let me slice again and see if it doesn't work. This is something that is still giving me some error. So what I could have done is to select, it means that this printer are likely not going to print my design, or I can just quickly come back here. It's oh, let me just scale it down a little bit. So I can just quickly come back here and do scale. I'm just trying to see these processes that we can encounter and probably how we can actually solve that. So I say 0.9, 0.9. So a little bit scale it down, is uniform. And you have something a little bit smaller and you see that has been applied. So I can come back here and see manufacture, still here. And let me slice again and see what comes out. Okay, parts are above the platform without support. Okay, so this really allows us to do what? To really tweak. So you've seen the warning sign telling you what exactly the issues and all that. So it means that if you print this stuff, it's actually going to fail because it's going to hang on air, but it's not stop dropping. So it's actually not going to come out a good print. So to solve this is the issue here. You see that it's not really on the best. So what I will do is just select this, put it clearance, and let it be on the bed, right? So, and I can now come back here and do my slicing. Yeah, so we have it, right? So we have it and we just sliced. So, and just this is a quick one. I'm going to take another process from the normal design to actually take us step by step of how we could actually do more. So back here, I have this. I can see the number of hours this should print on this printer around an hour, 30 minutes. So if I want to click here, I can do simulation of 2 parts. So this will actually give us like the current layer. I can play this to see the layer by layer, how this is done. First layer, second layer, how the addition goes in, how it keep building, and all that. So I could say this, get to the next one, keep adding layer by layer. If I want to make it faster, I could drag up here and, drag a little bit up to see how the layers are. Come and then continue playing. So you see how the additions of the layers, and the layer count is just 14, that's why it's quite small. The current layer height is 0.2. That's the layer height we used, to slicing it and all that. So the current time is at the point of 19 minutes. That's the current time here. So if I want to push in, since this is current, the layer count is 14. If I say 10 here, gives me, let me go back, sorry. Move back here. I say 10 here, see it's going to move into it, and you see, and then I start seeing the shapes of the infill. You see that this is now, well, you see how it's all tied together, how these things is coming into place. So that's how your things, all those things you went through into it, you see how the patterns are going. These are different shells that are there. This is the outer one. This is the outer one you see. This is actually the inner shells. You're seeing the whole hollows and all that. So this allows us to see better from what we are slicing and how it's all coming out. So you're saying that the layer height the layer height is 2 from the standard from what we selected. So let me cancel this, and I want to little bit iterate on the slicing of let me go back here and do a little bit more advanced slicing. So I will come back on the printer where we'll have the printing settings, which is this, and then select the PLA, just right click and say edit. So with this, it's going to open up a panel where I'm going to do more advanced. So we have the normal, this is like profiles, like body presets of each of them. So on the profile, you have it, and then under the strong, you have it. So now let's go to the, normal, you'll find the extrude, because the printer we selected has 2 extruders. So that's why it's asking us extrude 1, extruder 2. So we're using extruder 1, that's the right extruder 1. That's what it's using to print. So you're seeing the extrusion width 0.4, the perimeter extrusion and all this. So this is like all the, the settings for this extrusion. So if you go to cell, you're seeing shell count. So the shell count is how many shell is going to be inside, not the external shell count. So the shell count here, this is actually internal. So external shell count is just like one that goes through. So if I increase the internal shell count, it actually makes this thing stronger, but it also increases the time too. Number of layers, top layer, number of top layers. So this means that, okay, remember that you have an infill inside, and how many layers should you stop the infill and start building something, a little bit solid, so that you can actually have the surface a little bit more stronger than what the inside. But remember that the inside is using the infill pattern to actually make the products, strong. So you have the infill here. See the infill density is 25, so I can actually increase it to, let's say, if I can reduce it or increase the infill density is also what I mean by NC percentage. So you have it here. So if I'm increasing this, you see it's increasing, like it's 25. Let me, from here, this is where we are. Let me go to this point, strong, and go to infill. You say it's 50. So it means this particular thing, and you see the settings for the strong is setting for stronger functional part than this under the normal. So if I'm going to infill density, I'm seeing 25. Infill here is 50. So in the infill pattern, you're also going to see that there are different type of infill pattern, what we're using in Gyro. So if I'm using bed adhesion, skates or brim, so I'm using brim here, I can allow to get to be like number of layers of brim. I can set it here. If it's raft, it's grayed out because I choose brim here, so you can't. So so this is that, and then under the supports, what material do I need to print? Because of my printer has to extruder, I could comfortably assign support printing to, if I want to print with support, if this particular model is printing with support. So what I could have done is to assign this extruder 2 into as the support, the extruder that should print the support. Maybe I'm using HIPS or PVA, which are mostly like support materials is used, or you can use some parent material if it's one extruder. Like if I'm, since we're printing with PLA, so either we use PLA as support, or we can use HIPS, or PVA as support. HIPS actually is dissolvable in some solvents, and the PVA is dissolvable in water. So that's why they are kind of, those filaments are kind of really made specifically as support materials, because it can actually help you to remove those things, and also help you to get better surface finishing even with support than if you would have done if you didn't use support that are dissolvable in solvents, alcohol solvent, or in water. So you're also seeing that the speed here, you're also seeing that the support speed, the settings here are different, also as the settings here. So each of them, some are quite the same thing, some are different. But one major aspect that is quite significant to note is the share count. Number of parameters is 5. Under the share count here, you're seeing 2, right? So the infill, you're seeing 25 here, and the infill here, you're seeing 50. So, these are the major aspects of you increasing the strength of your material, of what you're going to come up. So if you're really going to want to get into something strong or very functional, print, you really want to increase the infill density. You also want to maybe a little bit increase the shell. And you also, if you were looking at situations where you want to talk about the layer height, you also want to talk about the layer height, whether you want to increase the layer height or you want to decrease the layer height, as depending on the type of surface finish that you want. So that's basically this for this, and then if let's say we switch from, this is it. So let's say we choose this, we want to choose a strong. So what we will do is we will come back here, double click. There is no error. Okay. So I can just come here. Sorry, I'll pick this and click OK. Edit notes. Okay. So I can actually switch from here. Excuse me. Yeah, so I can come here and switch assign body presets, right? And say, no, I want to be in strong, and assign this. So I'm switching from normal to strength. So to strong, so it means that it is using the profile strong. So all the settings that is then it means I need to slice, because I have changed, the settings for the slicing. Then I can come back here and generate. You will see that it's going to take longer time. Remember what we had there was 1 hour and 30 minutes. We are now seeing an approximate of 2 hours. And if I run here, I can also run the simulation and see how it also all plays out. Because I use same layer height, basically it gives me the same count. The only thing that actually changed magically is a shell, internal shell, count and particularly the infill density, right? Or the infill percentage. So it's really practical that we understand it. So next thing we probably need to do is just to go post process. I can just right click here and go to post processes, or I come here and I go to post process. So any of them is fine. So click on this. I already set up the machine. I already set up the post processor, the post processor for the machine. And then I'm look at the program number. I put like 5001. If I have any comments, I can add, but I didn't add those comments. So the output file is actually telling me this is the output file, but I say no. I want to change the output file to something where maybe I have an SD card or flash from the printer that I want to point. So let's say I'm selecting this, and I'm going to use this as output file, right? Or I'm going to just check this, pick, and then what I will do next is I'm not sending to create into browser. So what I can do next now is to click here, post process, and it sends to the following NC code associated posted. So automatically it gets to the flash, so I can just pick the flash, eject the flash, and be able to print. If you see that, you're going to see that here. This is the part, right? So that's the part I just printed. I'm just going to pull it, insert it into, let me share my screen. So that you can, so if you go to this, I think everybody can see my screen. Maybe sure now everyone can see my screen, right? Hello, can anyone see my screen?
Sorry, I was on mute. Yeah, yes.
Okay, so let me just stop sharing from my Fusion screen and just quickly show the file that we just exported now. So I'm going to do that now. So let me share that screen so you can see that particular file I just exported. So it's really something that you could also start understanding how that really adds up to trying to. Okay, we'll only share that screen, so but that's fine. So let me just go back, and so what I will do is to let me go back.
Sorry, the screen is not sharing at the moment.
Yes. Yes. So let me share my screen back. Okay, it's up now, right? So yeah.
Now we see the Fusion interface again.
Yes. So what I'm going to do now, let me just go through that process again, just to show us what we've exported. And we're really going to see, this is where the file is exporting, right? This is where the file just exported. So I can select this as a folder, and yeah, I'm seeing this particular file. So it's important for us to know that, we can select the points, especially if you're using SD card or your flash, there's plenty how to select the point to just write into your print and into the SD card or flash, and you have it there. So next thing I want just to go through this is let's look at a generative design. So we're still in design workspace. Some quite basic differences, but the major thing there is I want to talk about is support, because since the last Friday, we didn't kind of have a need to start having support because, it's just something flat and very, very simple. So now back to this, I can go back to manufacturing. And what I need to do is just the same routine, create my manufacturing model. That here is selected and go to setup. Come back here, select my printer. I need to make sure that I select, let me pick this, go to PLA, yeah. Select this, all right, and then select it so I can select everything at the same time. So you see this applies here and I'm good. So I move, you see it's out of the build volume, which is fine. So it's showing me red, that's why it's showing me red. So I can just pick my move and move into view volume and rotate. Okay, I can also drag here just to keep something close here. Just use something around here to just to centralize if I want to use manual centralizing. Or just this allows me to just position how I want to print or how I want to put it. And I have this. Let me come back here. So I have this. But remember that because of this surface, this is generative design, bracket. It's model that was produced through the generative design. So it's really like kind of complex shapes and all that. And that's what we're talking about, complex geometries and all that, or really where 3D printing really have so much of strength and all that. So if we have this, what I need to do is to come back here and say place on volume. But I want to add a clearance because of here, this point can't point well with a good support because look at this distance here and here, but there are also things that are a little bit high here, and then this space from here, if I don't add support, this space to do, if I don't add platform clearance here, this space from here to this point is not enough to build a support, so it's really going to have issues. So what I'm going to do is to add platform clearance, maybe let's say 5 mm. And I put a range, and I'm good. So it keeps it on top. And so next thing I will need to do is to add support. So remember we didn't add support in the last one. Here now we're adding support. So I come here to the solid volume. And what I need to do in the support section is to select the supported model, which is this. So sorry, not this. Sheets. I need to select everything. Yep. And then the support overhang. Okay. I want to have a support overhang, let's say 45. So spaces to avoid, just don't add support here, right? So I click here, I say here, this is small, so don't add support for me. Remember what we said earlier on, so I'll just come back here. Say, do not add support on this face or face. Do not add support here. Sorry. Let me remove here. Move in here, move in here. Move in here, this and this. So I don't want for support to be added here. So actually allows me to print, and because it's small, it can actually print. But if I print with support, kind of tiny. So if I want to add maybe distance between other support, to other support, so I want to maybe kind of put spaces and all that if it's needed, but I don't really need it. So I can just click OK, and it will start up the process here to add support. So you see as building support. Remember I selected this and this, or this building support now. So build support, if report comes out fine, then I should proceed, should give me green. If it comes out, if it failed, adding support, it should give me red. If it comes out yellow, it means there's some warnings I need to address for me to really get the right support. So it's adding support, processing for the support, probably takes a few seconds or more, about 10 seconds or 20. It's just to add the support in here because this is quite complex. So you have a lot of, we have to analyze where to add support, where not to add support, and all that. But the only thing I said, do not add support here, these places, and all that. So it really allows us to make sure that, so just be sure that not everything that you are printing that you need to add support. It's very important for you to know that while you are adding support, add support when it's necessary. because it's not really visible for us to print this without support, right? It's quite complex, a whole lot of things coming in. So now it's very important for us. Our support and iron support is also quite important. So, but again, when you can print without support, please go ahead and print without support, because it actually saves you material, because it actually helps you to reduce material waste. It also saves the material you're going to spend, reduce the material you're going to spend, in printing. It also reduces the time, because those time it will take to print the support is also part of the time it's going to calculate for the final printing. So means that your printing support is also an addition of adding more time to the printing process. So increasing material you're going to spend, the filament you're going to spend to print, you are also spending more time for printing, and you're also going to be experiencing more rougher surfaces in each of the places where the support is. So support is important to use if it's needed, but if it is not, please do go ahead and don't use support. So it's really going to quite take into account more time than expected, but I think we'll just kind of wait a bit more, just slicing, because honestly, there's quite a whole lot of support. And when this thing comes out, you actually understand why it's quite taking this time. So it's really, so just go through this, you see a whole lot of places where the support, because this is like really organic, right? So it's something that you can push into the stuff and you really print and get out what you want. So it's coming up, and it's almost there. Yeah. So it's almost there. So I think we should just, next thing we'll probably need to do is just to do our final slicing after support is added, and then we are good to go. So basically, while you are adding this, you can also go to the printing settings to change whether you want to change from normal to strong, or you can even also modify each of those settings. Oh, my normal, I don't want my normal to be 25 degrees. In field, I want it to be 20 or 10. You can do that settings, right? So you can actually allow you to go through that process and do that setting. So yes, so it's something that we can actually go through. So why is kind of taking a little bit more time than I expected? But why is doing that? I think we can actually pause a little bit. If there are questions, I can attend to one question or more, and then we'll come back and then finalize on this, and we can have all our questions asked. I think at this point, you definitely will have a lot of questions to ask. And so I don't know.
Yeah, so I actually, there hasn't been any questions in the chat and Q&A, but I, like before, would definitely encourage you while this is working in the background, if you have questions on what you've seen, or if there was something that you didn't see so far, then we have a good opportunity now to take some of those. So we'll just give everyone a few seconds to think about questions, and yeah, please use the chat or Q&A functions for posting a question.
Okay.
Yeah, there's already a first question. I guess you've seen it also.
Yes. Can some of these processes be applicable to laser cutting too? So laser cutting is not an additive manufacturing process, right? So I just wanted to point that out. So fundamentally, laser cutting falls within the subtractive, right? So it actually removes material. We want to cut something to a particular shape. So maybe you're bringing an ABS, maybe 2 mm, 3 mm, or 1, plastic, or you're bringing what's it called, sheet metal of 1 mm, 0.8, 0.5, 0.6 mm, and depending on the type of this laser cutting you're doing, whether you're doing plastic, or the metal, which most common one is metal. So metal, goes through sheet metal. So it follows the rules of sheet metal fabrication. So because laser cutting works with sheet metals like bolts and all the way you can cut and get them into shape. And it's particularly metals where you can also cut and fold, like your generator enclosures to your PC, all the old desktop computers, PCs, they're all sheet metals. They are kind of cut, drilled, all the ports where you see there, they're all sheet metal drilled and folded and all tied up. So that uses laser cutters. Laser cutters can come with, can either be uses water, some like water in quite high pressure. You can also use light, laser, that's kind of the laser part now. It's like light, beams to actually cut. Some can also use water and all that. So that's where the whole thing, some I think I've seen also ones that use lightning of coming from tin, and they're using it to heat up to cut certain things, but in a very high concentrated focus. So yes, so it's really something that we can actually look at. But yes, it's different. It's not the same. But just like I emphasized before now, it's important for you to know that for each of them, they are manufacturing technology. Now, something I want to point out, the most underrated globally, not just in Africa, section and design is design for manufacturing. A lot of people do not understand this thing, and which is very, very important for you to design, for you to be very powerful, very good, very, really becoming somebody who's quite grounded in design. You really need to start understanding the design for manufacturing. So for whether it's for injection molding, for additive manufacturing, it comes to the additive manufacturing, you're also looking at different types of additive or different technologies and different manufacturing. If it's if you're looking at even injection molding, there are also whether it's plastic injection molding, the blow mold, there are different type of molds, mold machines, and all that. If you're also looking at maybe laser cutting, you're also going to consider different aspects of laser cutting, whether it's beam, whether it's water and all that. So each of them have quite similar, for each of the manufacturing process. If it's laser, different technologies will have quite similar, but categorically that will be different from additive, they will be different from injection molding, they will be different from casting, they will be different from forming and all that. So there are all different considerations that you really have to put in place, to really, so that really is important. So back to this, so we really have our support all come out. So you see why it's really took that time. So see that the support is all added in areas. So you start seeing that these surfaces where the support is built from, you get rougher than the surfaces where there's no support. But we can't really do much. But the best way we could have done this is to use a different filament, since we have our printer is 2 extruders. Unlike most printers, this printer is 1 extruder. The printer we selected is 2 extruders. So what we could have done is maybe use PLA or ABS. Let's say maybe ABS for printing and then use for PVA, or the other printer to print support. So these are things that we could actually, really explore in that regard. So we can now go ahead and do the final slicing. So
sorry, Felix, sorry for interrupting you, but I think you're kind of live answering. I don't know if you saw the question that came in, but you're kind of answering that now. But just that there was a further question about the model on the screen, that there's some tiny parts, and how do we ensure strength and stability of these sections? And I think you just wanted to mention that was a question, since it kind of relates to partly what you were saying.
Okay. The product on the screen seems to have some tiny parts. How can we ensure the strength and stability of it? So now for this, I think one of the parts that we really want to ensure is the aspect of using higher tiny. First, there are 3 things you need to put into consideration. One is the smaller layer height. Really is important, because remember that the smaller layers can print higher details more accurately. So maybe instead of using 0.2 generally of layer height, you probably want 0.2 mm, you probably want to use 0.1, or even a good number of FF factory printers now can actually print with 0.05. So with those tiny details and all that, you really want to use 0.1 to 0.05, depending on the capability of the printer. That's one. Secondly, is also to increase the strength. You also want to print with higher infill density. So instead of printing with 5, sorry, instead of printing with 15 or 20 infill density, you probably want to print with 50, 70, 80, right? So it also allows you to do that. So again, another aspect of it is you can also do is to increase the share count, internal share count of this. That can also really go a long way in making sure that you come out with fine prints. We also come out with stronger prints that will not just be quite breakthrough and all that. So increasing the infill density is important. And also, and again, depending on the type of, you also want to play around with the infill pattern to know which of them is fitted for what applications and all that is also quite very critical. So you have this already done, and then we can also run this processing, same thing we did before. And it's going to go, I think, another question. Okay, response. So that's fine. So we have this, and I think we'll quite, in time of really get to really maximize time to PM here, that's 3 p.m. South African time. So I think so we can really spend more time for the question and answer, and then we can really go through them. So one is you are not seeing the layer count is 445, like children one just had 14. So it really means that this will really spend quite a lot of time, and you're seeing 2 hours this month. And for the layer height is around this. So it's really something we need to truly understand. And it's adding faster, looking at this. So yeah, I don't know if there are further questions. I really will be happy to answer, more further questions that you have that you can actually do. So what you need to do at the moment, you can push the process here, or you're satisfied to how it is and all that. And you can push the process and you will have something important. So in here, just to point out, I can drag here, around here, you will see the support, which is this color. What we're printing here is the support, right? You will see the actual parameters. So if I push this up a little bit, so if you push up, let me pause and do a little bit push up. So then, as it's slicing, you start seeing the outer perimeter, the inner perimeter inside. So seeing that thing coming in. Zooming now, you can see that it's all coming out. How it's all slicing the infill, the bridge. If there's any bridge here, the rafts. If you added rafts, brim or skirt or brim, if you added. So these are like, basically what it shows us here. This color, this thing is actually what it's pointing out here. Actually, not okay. This is this is that. We can really experience and understand better how these things truly works. So yes, I don't know if there are 4 further questions, and let me tie this down like this, and we can please keep your questions coming.
Yeah, exactly. So thank you for taking us through this part. And yeah, and as I said, we now have blocked out some time to handle questions that you may have on what you've seen, and feel free if there was anything that you felt we didn't address earlier today or even tomorrow, yesterday, then feel free to throw that in as well, and we'll do our best. But particularly while we have Felix available to us, if you have any further questions about Fusion 360 or the model we've seen, the workflow, feel free to use the Q&A and chat. And there's immediately a question that's great. So it's about how we can reach out to you, Felix. And I know that my colleagues are going to put your contact details in the chat window. And I assume that you're happy for people to connect in case they want to review any collaboration or other opportunities, since you're also your day job is obviously to deliver training and support and services around these tools.
Yes, so I'm quite very happy to connect and people who want to really support or help and all that to ensure a crossing of adoption, not just because I'm quite really passionate about Fusion because it actually helps into that CAD/CAM, CAE, PCB, and all that kind of one platform. You can actually really go into product development. So yes, you can reach out to me and on LinkedIn, just same name as it is. I think I'll really be more responsive, more on LinkedIn than probably on Facebook or Twitter or Instagram. So yes, I'm there, but if you really want, since it's really work professional stuff, please reach out to me. I'm more active there and I'm more responsive too. So you can send me connection requests and then we can take it up from there and then we can see what we can do. So yes, so for collaborations or support or questions and all that connects, I'm really quite open for that. And I think it's something that will, that will really go a long way in making sure that if we truly adopt Fusion 360 in Africa, because it is one particular tool for me that really makes it quite that the two tools I think that really will help democratize product development in Africa is software tool I look at is Fusion, and the second is that the manufacturing technology is additive manufacturing. Why? Because Fusion is just one platform that you can really get into. It allows you to work remotely. You can actually have access, for small teams, you can actually support that too. And it's quite very affordable compared to some other softwares out there. It's quite very, very affordable. I think it's the most affordable to these products you have out here. So it's really something that I really want. And then looking at additive manufacturing in Africa, we don't have so much of a manufacturing equipment and all the sophisticated ones that probably we need for us to kind of transition to additive or kind of equip additive. We probably want to abandon. Doesn't necessarily need to abandon, but in Africa we have almost very insignificant number when it comes to manufacturing output. So 3D printing is really going to cut that cost down from tooling. And 3D printing is not just for final parts. It's not just for test and fit. It can also come into tooling. Today we have 3D printed molds, metal 3D printed molds that you can print, design your product. 3D print, yes, you want to get into the injection mold, but if instead of going through this machining quick text molds, you machine the mold, you can actually put in weeks, 1 or 2 weeks, and then get your mold, print it, and then ship into the injection molding machine where it can actually produce like thousands of copies. So you can actually reduce that so 3D printing or additive manufacturing can come into different points of your process. So it mustn't really be like, it must be only for final production. It can be for proof of concept. It can be for test and fit. It can be for functionality. It can also be for tooling process. So to help, facilitate some other, production manufacturing technology processes to facilitate that tooling process. Something really important. I think that this tool is something that will really power the ecosystem in Africa, and will help democratize product development in Africa, because we need to start thinking about how products are made before we start even thinking the supply chain aspects. Where is the part going to be coming from? The one are going to source in the market, where the talent is, how many talents will they have out there to going to be? What are the machines we have available? What are the ones that we can do it locally and the ones we can do outside? So there's a whole lot of mix coming out in the hardware space in manufacturing, which is not really that, which is more harder as hardware as compared to software, how to do with supply chain and logistics and a whole lot. So yes, I think this tool will really help that really cut down that entry point. It's also going to help in facilitating that progress and take us to further. So really we start acting meaningfully into the general productions as what, manufacturing as what other continents and what other countries are actually doing at the moment. And looking at what, Australia has done in the last 3 years, having over 50 3D printing farms, and looking at the transition that was done, where Australia was, and how they adopted 3D printing and really becoming significant in the manufacturing process. I think is also something that Africa should, really going to benefit Africa as we kind of look into that direction and really kind of adopt and keep advancing in more mature and 3D printing technologies, the professional, the metals, and the more industry standard materials too. Thank you. Over to you, Thomas.
Yeah,
I think there's no further questions.
No, thank you so much. And it doesn't look like there are any further questions at the moment. So I think we will, once again, thank you so much for being with us and showing us this super exciting workflow. What I propose we do now is that we go through just a few next steps in terms of our event here. And then, as you heard from Felix, he's available to connect through LinkedIn if you have any if you want to connect with him, especially if you're interested in learning more about Fusion and potentially taking a full training with him as well, then that's a great opportunity. So thank you, Felix, for being with us this afternoon.